In the simulation on the left, we're doing the calculations for an energy balance when we fill a tank. And so the idea is we start with a tank that contains an ideal gas. We're given its pressure and temperature. And then we have a flowing stream at higher pressure and a temperature that can be varied. So the line temperature can be changed. Likewise, the tank temperature can be changed and the tank pressure can be changed. And the question is, when we open this valve, let the system go to equilibrium adiabatically, so the tank is well insulated. We open the valve until the pressure gets to 15 bar, and then we close the valve. What is the temperature inside this tank? Is it between 150 and 200 C? Is it above 200 C? Is it below 150 C? And so we have to solve an unsteady state energy balance, and that's what the simulation does. So we select play here to make the valve open. We also can select water in a little more complicated system. In this case, we start with a vapor-liquid equilibrium mixture, and we can change the pressure. We can't change the temperature because it's a vapor-liquid equilibrium mixture. Once the pressure is fixed for water, then the temperature is fixed. And then we have a flowing stream of steam. So we're adding more water. And we can change the pressure in the line. We can change the temperature. And the question is, what is the final condition when we open the valve? Again, we click here to open the valve, and we're carrying this out adiabatically. So let's look at the simulation to see the behavior, the results of solving this unsteady state energy balance. So here's the simulation for ideal gas, nitrogen. And when I select play, the valve opens and then closes once we get to the same pressure as the line pressure. And let's reset that so we can notice we're starting at 200 degrees C. This is 150 degrees C. But notice the final temperature is higher than either one of these, 300 degrees C, because we're doing work when we start compressing this gas. Remember, this is insulated, so it's adiabatic compression, and the temperature goes up. And this temperature is calculated from that unsteady state energy balance. If we instead start with water in vapor-liquid equilibrium, and I select play, now the pressure goes up to 10 bar. 180 degrees C is the saturation temperature at 10 bar, and we have a vapor-liquid mixture at the higher temperature. So notice that what happened was we started out with 21% vapor, and we ended up with 39% vapor. So a lot of the energy went into vaporizing the liquid, some went into also raising the temperature. And so this unsteady state energy balance is important for understanding first law of thermodynamics.